In a balanced three-phase system, the neutral current is theoretically zero because the currents in the three phases cancel each other out. However, in a single-phase system, there can be a neutral current if the loads are unbalanced. In a single-phase system with balanced loads, the neutral current is also zero. A balanced load means that the loads connected to each phase draw the same amount of current. In this case, the currents flowing in the two-phase conductors cancel each other out, and no current flows in the neutral conductor. Take the example of a recreational vehicle campground with 120 volt, 30 amp hour receptacles. One can assume the loads are balanced. This is because the receptacles are likely used for a variety of appliances and devices that draw equal amounts of current. Therefore, in this case, the neutral current is zero, and you can ignore it when calculating the voltage drop. Voltage drop calculations are correct for the 120 volt and 240 volt feeders. However, it's important to note that the 120 volt calculation is only applicable to the single-phase loads. The 240 volt calculation is applicable to any loads connected to the 240 volt panel. If the loads are unbalanced, there will be a neutral current. However, it is challenging to accurately calculate the neutral current without knowing the specific load characteristics. In practice, it is common to assume a neutral current of 25 to 50% of the phase current. Assuming balanced loads, you can ignore the neutral conductor in the voltage drop calculation. The voltage drop calculation for the 240 volt feeder is appropriate for sizing the feeder for the distribution panels. If the loads are unbalanced, you can estimate a neutral current of 25 to 50% of the phase current and adjust the voltage drop calculations accordingly. To delve deeper into the concept of balanced neutral current, it's crucial to first establish a solid understanding of single-phase and three-phase power systems. In a single-phase system, power is delivered using two wires, typically a hot wire and a neutral wire. The voltage between these two wires fluctuates in a sinusoidal pattern. Electrical loads connected to this system draw current that alternates in direction with the voltage. In contrast, a three-phase system utilizes three hot wires, each carrying a voltage that is offset by 120 degrees relative to the others. This arrangement provides a more consistent and efficient power delivery compared to single-phase systems. Now, let's examine the scenario where loads are perfectly balanced in a three-phase system. Imagine three identical loads, each connected between one of the hot wires and the neutral wire. If the voltage and impedance of each load are exactly the same, the current flowing through each phase will also be identical. Due to the 120-degree phase shift between the currents, they effectively cancel each other out at the neutral point. As a result, there is no net current flowing through the neutral wire. However, this ideal scenario rarely occurs in real-world applications. Loads are seldom perfectly balanced. For instance, in a commercial building, some circuits may power lighting, others may power computers, and still others may power machinery. Each of these types of loads would draw different amounts of current and will have different power factors. These imbalances in current draw lead to a non-zero neutral current in a three-phase system. In a single-phase system, the concept of balanced neutral current takes on a slightly different meaning. Consider a 120/240 volt single-phase system commonly found in residential buildings. This system consists of two 120 volt hot wires and a neutral wire. Loads can be connected between either of the hot wires and the neutral, providing 120 volts, or between the two hot wires, providing 240 volts. If the 120 volt loads connected to each hot wire are equal, the currents in the two hot wires will be equal and opposite, effectively cancelling each other out in the neutral wire. Similar to the three-phase case, this perfect balance is seldom achieved in practice. Appliances and devices are switched on and off at different times, leading to imbalances in the current flowing through each hot wire. These imbalances result in a neutral current that is proportional to the difference in current between the two hot wires. In the specific example of a recreational vehicle campground, the electrical loads are likely to be diverse and unpredictable. Each recreational vehicle may draw a different amount of current depending on the appliances and devices being used. Furthermore, these loads may fluctuate throughout the day as people turn on and off lights, air conditioners, and other equipment. Given this variability, it is highly unlikely that the loads will be perfectly balanced. Therefore, a neutral current will almost certainly be present in the feeder supplying the campground. The magnitude of this neutral current will depend on the degree of imbalance between the loads connected to each hot wire. To accurately determine the neutral current, it would be necessary to monitor the current flowing through each hot wire and calculate the difference. However, in practice, this is often not feasible. Instead, engineers typically make assumptions about the expected load imbalance and size the neutral conductor accordingly. Electrical codes, such as the National Electrical Code, provide guidance on sizing neutral conductors based on the type of loads being served. For example, for circuits serving mostly nonlinear loads, such as electronic devices, the NEC may require the neutral conductor to be sized larger than the hot conductors to accommodate harmonic currents. These harmonic currents are produced by nonlinear loads and can significantly increase the neutral current. Now, let's address the question of whether the neutral conductor can be ignored when calculating voltage drop. In general, the answer is no. The neutral conductor carries current, and this current contributes to the overall voltage drop in the circuit. The voltage drop is the reduction in voltage that occurs along the length of a conductor due to its resistance. This voltage drop can negatively impact the performance of electrical equipment, causing lights to dim, motors to run slowly, and electronic devices to malfunction. To minimize voltage drop, it is important to use conductors that are large enough to carry the expected current without excessive voltage loss. The voltage drop can be calculated using Ohm's law, which states that voltage drop equals current times resistance. The resistance of a conductor depends on its material, length, and cross-sectional area. Longer conductors and conductors with smaller cross-sectional areas have higher resistance and will therefore exhibit greater voltage drop. In the case of a single-phase circuit with the neutral conductor, the total voltage drop is the sum of the voltage drop in the hot conductor and the voltage drop in the neutral conductor. Therefore, ignoring the neutral conductor in the voltage drop calculation will underestimate the total voltage drop and may lead to undersized conductors. However, there are some specific situations where it may be acceptable to neglect the neutral conductor in the voltage drop calculation. For example, if the loads are known to be very well balanced and the neutral current is expected to be very small, the voltage drop in the neutral conductor may be negligible. In this case, it may be reasonable to ignore the neutral conductor in the voltage drop calculation. However, it is important to exercise caution when making this assumption and to verify that the neutral current is indeed small. It is generally better to err on the side of caution and include the neutral conductor in the voltage drop calculation to ensure that the conductors are adequately sized. The voltage drop calculation for the 240-volt feeder can be used for sizing the feeder for the distribution panels. However, it is important to consider the impact of unbalanced loads on the neutral current. If the loads are significantly unbalanced, the neutral current may be substantial and the neutral conductor may need to be sized accordingly. In summary, the balanced neutral current is a theoretical concept that applies to both three-phase and single-phase systems. In a perfectly balanced system, the currents in the hot conductors cancel each other out in the neutral conductor, resulting in zero neutral current. However, in real-world applications, loads are seldom perfectly balanced, and a neutral current is typically present. The magnitude of this neutral current depends on the degree of imbalance between the loads. It is important to consider the impact of neutral current when sizing conductors and calculating voltage drop. Electrical codes provide guidance on sizing neutral conductors based on the type of loads being served. In some cases, it may be acceptable to neglect the neutral conductor in the voltage drop calculation, but it is generally better to err on the side of caution and include it to ensure that the conductors are adequately sized. To further elaborate on voltage drop calculations, let's examine the factors that influence voltage drop and the methods used to determine the appropriate conductor size. The voltage drop in a circuit is directly proportional to the current flowing through the conductor and the resistance of the conductor. As mentioned earlier, Ohm's law states that voltage drop equals current times resistance. Therefore, to minimize voltage drop, it is necessary to either reduce the current or reduce the resistance. Reducing the current can be achieved by using more efficient electrical equipment or by distributing the load more evenly across multiple circuits. Reducing the resistance can be achieved by using conductors with larger cross-sectional areas or by using conductors made of materials with lower resistivity, such as copper. The National Electrical Code provides tables that list the ampacity of various conductor sizes. Ampacity is the maximum current that a conductor can carry continuously under specified conditions without exceeding its temperature rating. When selecting a conductor size, it is important to ensure that the ampacity of the conductor is sufficient to carry the expected load current. However, ampacity is not the only factor to consider. Voltage drop must also be taken into account. The NEC recommends limiting the voltage drop in branch circuits to 3% and the voltage drop in feeders to 5%. To calculate the voltage drop, it is necessary to know the length of the conductor, the current flowing through the conductor, and the resistance of the conductor. The resistance of a conductor can be obtained from tables published by conductor manufacturers or from online calculators. These tables typically list the resistance per unit length of various conductor sizes and materials. Once the resistance is known, the voltage drop can be calculated using Ohm's law. If the calculated voltage drop exceeds the recommended limits, it will be necessary to increase the conductor size. Increasing the conductor size will reduce the resistance and therefore reduce the voltage drop. It is important to iterate this process until the voltage drop is within acceptable limits. In addition to using larger conductors, there are other techniques that can be used to reduce voltage drop. One technique is to use multiple parallel conductors instead of a single large conductor. This effectively reduces the resistance of the circuit and therefore reduces the voltage drop. However, it is important to ensure that the parallel conductors are properly sized and installed to ensure that the current is evenly distributed among them. Another technique is to use voltage boosting transformers. These transformers can be used to increase the voltage at the load end of the circuit, compensating for the voltage drop that has occurred along the length of the conductor. However, voltage boosting transformers can be expensive and may not be practical for all applications. In this specific example of a recreational vehicle campground, voltage drop can be a significant concern due to the long distances involved in distributing power to the various recreational vehicle sites. It is important to carefully calculate the voltage drop in the feeders and branch circuits and to select conductor sizes that are adequate to minimize voltage drop. The use of voltage boosting transformers may also be considered in some cases. Furthermore, it is important to regularly inspect the electrical system to ensure that all connections are tight and that there are no signs of overheating. Loose connections and overheating can increase the resistance of the circuit and exacerbate voltage drop problems. In addition to voltage drop, it is also important to consider the impact of harmonic currents on the electrical system. Harmonic currents are produced by nonlinear loads, such as electronic devices and fluorescent lighting. These currents can distort the voltage waveform and can cause a variety of problems, including overheating of transformers and conductors, malfunction of electronic equipment, and increased energy consumption. To mitigate the effects of harmonic currents, it is important to use harmonic filters and to ensure that the electrical system is properly grounded. Harmonic filters are devices that are designed to block harmonic currents from flowing through the electrical system. Grounding provides a low impedance path for harmonic currents to flow back to the source, reducing the voltage distortion. In the case of a recreational vehicle campground, it is likely that there will be a significant number of nonlinear loads such as electronic devices and air conditioners. Therefore, it is important to carefully consider the impact of harmonic currents and to take steps to mitigate their effects. This may involve the use of harmonic filters and the installation of a robust grounding system. Moreover, surge protection should be in place to protect electronic equipment from voltage spikes that can occur due to lightning strikes or switching events. Surge protective devices, or SPDs, are designed to divert surge current away from sensitive equipment, preventing damage. They are typically installed to the service entrance and the distribution panels throughout the electrical system. Regular maintenance is key to ensuring the continued safe and reliable operation of the electrical system. This includes periodic inspections of conductors, connections, and equipment, as well as testing of protected devices such as circuit breakers and ground fault circuit interrupters. Any damaged or worn component should be replaced promptly. For recreational vehicle campgrounds, special attention should be paid to the condition of the receptacles that serve the recreational vehicles. These receptacles are subject to heavy use and exposure to the elements, and they can become damaged over time. Damaged receptacles should be replaced immediately to prevent electrical hazards. Electrical safety is paramount in any electrical system, but it is especially important in recreational vehicle campgrounds due to the presence of diverse users and the potential for exposure to the elements. Ground fault circuit interrupters should be installed in all branch circuits serving recreational vehicle receptacles to protect against electrical shock. In summary, understanding the principles of balanced neutral current, voltage drop, and harmonic currents is essential for designing and maintaining a safe and reliable electrical system in a recreational vehicle campground. Careful planning, proper installation, and regular maintenance are all critical to ensuring that the electrical system can meet the demands of the campground while protecting the safety of its users.